Gas chromatography is a really quick and easy way to assess the purity of a sample, especially in the case of mixtures. Typically, the mixtures are a mixture of volatile components. And so we're going to talk about the various phases of gas chromatography, how it works, and how it's used to calculate the percentages of the components in a mixture. And we've really we're lucky to get a gas chromatography instrument that's hooked to a mass spectrometer. Although I'm not going to be talking about how mass spectrometry works, this was a donation from the crime lab in town, and it's a real workhorse for us. In fact, we just recently completed column chromatography, and I've already passed the samples through the column just to assess how well we did at column chromatography, but also distillation is what we're working on right now. So let's take a look at how gas chromatography works. And by the way, you can skip ahead in this video and to the end. You know, if you just want to see the calculations, that's towards the end part of this talk today. So there's a couple phases to gas chromatography. First of all, we'll briefly talk about sample preparation. So how do you prepare the sample for injection into the gas chromatograph? Sample injection is the part where the needle or the syringe is literally injecting the sample. Column separation, detection, and then finally collection, which I can just address this right now. Typically, we don't collect samples on the other side of gas chromatography, so it's a one-way trip for our mixture samples. But at the same time, we don't waste a lot of sample because we're talking about microliters worth of sample injected in the gas chromatograph. It's a very sensitive instrument, so that's not too much of a worry. There are people that actually do collect the samples. That's called preparative gas chromatography, but that's infrequently done. Most people don't do that. Okay, so here's the first phase of gas chromatography. You prepare your sample. Most samples are run as a neat sample. Typically, they're liquid mixtures with a couple of components that are reasonably volatile, which means that you can just apply a little bit of heat and they go into the gas phase. If we have to dilute the sample, pentane is probably the best one of choice. Pentane is very non-polar, and it's got a relatively low boiling point, so it tends to come through the GC very quickly, in fact, quicker than most components of the mixture, and that's really convenient for us in our analysis. So if you have to dilute, pentane is probably the best choice, or some other solvent that's very volatile and it doesn't have a lot of moisture in it. Solid samples can be run, but it's a little bit tougher for solid samples because the gas chromatograph oven has to be heated up quite substantially, but you can do it. They have to be dissolved in pentane first. In fact, our results of column chromatography, we dissolved in pentane, and then we put it into a little GC vial. And that's where the sample goes in a little GC vial, also known as an auto sampler vial, and then onto the sample tray at the appropriate ID or slot. Now, once it's on the tray, most of the time students don't see this process, but I program the auto sampler, and once the run begins, a little robot arm picks up the sample and places it places it near the syringe, and the syringe typically pre-rinses with the sample. A couple times they may pre-rinse with pentane a couple of times before pre-rinsing with the sample. But eventually what it does is it injects 0.2 microliters of the sample into the injection chamber, and that's really a tiny amount, and it's really quick when it does inject. So once inside the injection chamber, the sample is immediately volatilized. It's really hot inside the injection chamber, so that just becomes volatile in an instant. And the vapors themselves from the mixture are frequently diluted with the carrier gas. There's always a carrier gas that's passing through the instrument. We're using ultra-pure helium right now, but it's getting expensive, so some people use hydrogen gas, which is a lot more risky. So there's a bigger danger of explosions with hydrogen, but for now we're using helium. And this is called a splitless injection when the sample is diluted. In fact, with liquid samples, this is always done. I always dilute the samples with the carrier gas. And then all the total mixture then eventually reaches the gas chromatography column, and this is where the separation of the mixture occurs. These columns are really long. In fact, ours uses what's known as a capillary column. You'll see some discussions in the textbook if you're reading of pack columns and this kind of stuff, but these days the modern column is just a capillary column. It's not packed with anything as far as I know. It's 30 meters long. It's really tiny, really thin, and the compounds are passing through this column, and typically they're separated by boiling point, and so the lighter, lower boiling point compounds come through very quickly, and the heavier compounds come through more slowly, and that's exactly where the column separation occurs. And that's the whole point of gas chromatography, is we're trying to separate the components of a mixture and detect them one at a time as they leave the column. So we're going to be talking about the detectors that are common to detect these samples as they come off the column. Probably the most ubiquitous detector in gas chromatography is called a flame ionization detector. Our older gas chromatographs use this type, and a lot of GCs out there use this type. Simply put, you just have a hydrogen flame that's burning at all times at the end of the column, and as the samples leave the column, they're immediately combusted. And based on how much of the compound is coming out at any given time, immediately combusted, that creates a current. You know, it's kind of hard to describe, so I don't want to get into the gory details of this, but based on how much current there is, that's proportional to the sample size. So we can quantify how much is coming off the column at any given time, and the computer, of course, is registering current versus time. Now, our modern instrument uses a mass selective detector, MSD for short. That's essentially a mass spectrometer. So not only can we detect the samples coming off the column, but we can also attempt to identify them too. And that's the real advantage of a mass spectrometer versus a flame ionization detector. The way you figure out what the compound is for flame ionization is you have to run a known mixture of known reference compounds. You don't have to do that with mass spectrometry. So that's really convenient for us. That GC mass spec that we have is really a workhorse. It's really useful to us. Now, like I said, FIDs work by combusting the components. Mass spectrometry is something I'll talk about next semester. I don't have the time to discuss the gory details of mass spectrometry, so that's going to be a full discussion next semester. But again, it detects and it also identifies what the compound is coming off the column at any given time, so that's really useful. Now, once the columns are detected, of course, a computer is hooked to this, and the computer is registering the abundance in the case of mass spectrometry or the current in the case of FID. In either case, we're plotting on the x-axis, we're plotting time, sometimes known as the retention time, versus abundance or current, whatever is appropriate. And we're going to see these little peaks eventually come out in the chromatogram, and the area underneath the curve is proportional to the amount of component in the mixture. So the bigger the peak and the greater the area, the more of that particular compound is in the mixture. And that's pretty much what we use gas chromatography for, is quantifying the amount of any particular component in a mixture. Unfortunately, it's not just that easy. Unfortunately, the components of a mixture do not ionize equally. So in both cases, in both mass spectrometry and flame ionization, there's some sort of ionization occurring, and compounds just simply don't ionize in the same way. So what's unfortunately necessary is that we have to pass a mixture of the same components of the mixture through the column, through the detector, and assess what the response factors are. Response factor is essentially just a quantitative measurement of how well samples ionize. And that has to be done once. And typically, Doug Manning or I usually measure these for you, and then I just give these values to you. And then I'm going to show you how these get incorporated into the calculation later. But they have to be measured every time we do a gas chromatography run. In fact, this year I was about to work up the numbers, and I thought I could get away with last year's response factors for the same compounds, but it turns out they've changed, probably because the column length has changed a little bit. We just started up the GC again, so we're going to unfortunately have to remeasure these things. Now, like I said, compounds, not all components ionize in the same way, so it is necessary on a regular basis to measure these response factors. And once they're known, and once you've run your own sample, the calculation, just to go through this really quickly without explaining much, to go through this calculation, the way you calculate, let's say you have a mixture of two components, A and B. The way you calculate percent A is you have to take into consideration the response factor for A, and that was previously determined by a separate experiment, times the current area for A in your chromatograph. So these have to be multiplied together, divided by the total sum of the response factor of A times area A plus component B response factor times B area. So this is kind of a tedious calculation. That's why I've eventually set up a web page that makes this a whole lot easier, but I still wanted to talk about how this is done. So in this type of calculation, it's almost like your standard percent A calculation, except you do have to incorporate these response factors to make it really work well. Same goes for percent B. Now, that's assuming that there's two components. Of course, if there's multiple components, like 3 or more, then you just keep repeating this calculation and add everything together in the end. Okay, so that's how you calculate the percent A and percent B, and that's ultimately what we're usually after in a gas chromatography experiment. For example, in our column chromatography, we did GC to assess the results. In a perfect world, test tube number 2 contain 100% of fluorine, and test tube number 3 would contain 100% of the second compound, which is fluorinone. In most cases, though, we don't get perfect separation, so you're going to calculate for both test tube number 2 and 3 what the percent of fluorine and fluorinone is for both samples. Some of you got lucky. Some of you did the column chromatography really well. It is 100% for each. Distillation is the same thing. So we've got 2 components of a distillation mixture. You distilled it, and I definitely expect not perfect results. You're going to have to do this calculation for both components of your mixture in either case. Okay, so that's the calculation. Now, just in picture form, really quickly, I'm going to show you the same thing that I discussed in words. The first step in gas chromatography is you've got a sample mixture, and it goes into one of these little GC vials. Typically, we're working with liquids, a neat sample. We typically don't do a dilution unless we have to. We have a solid or something like that. And then you sign for a particular auto sampler or spot. You put it onto the sample tray. And like I said, a little sample arm swings around, grabs the sample, places it about here. This is the syringe, and the syringe pre-rinses with the sample, and then eventually it injects into the injection chamber. And like I said before, the injection chamber is really hot, so the sample is immediately volatilized inside there. And right at this point, it goes into a really long column, okay, 30 meters long, until eventually it comes out and it's detected by some sort of detector. That could be a flame ionization detector, or it could be a mass spectrometer. That's the case with us, mass spectrometry. And that's, of course, hooked to a computer. And on the computer, what we have is a plot of the retention time, abbreviated RT, versus the signal, whatever that may be. That could be abundance, or that could be current. And I've got a kind of a representation of this over here, but we get, we see these little peaks, and the area underneath the curve that we see, and we can manually integrate these things on the computer, is proportional to how much sample is coming out. So let's take a look at that now. So this is what a typical chromatograph looks like, is again, the retention time in minutes versus the abundance. And so the retention time of A is, right about here. It's, 2 minutes, 3 minutes, whatever it is. And then B is a little bit further along. One assumption that we make about this mixture is that A has probably got the lower boiling point. That's a fairly safe assumption about this mixture, and B has got the higher boiling point. They've already been separated, so they're detected one at a time as they come off the column. I just talked about the calculations. So A, you have to adjust the area of A by its response factor, and you have to do the same thing for B. You have to multiply by its response factor, and then in the end, percent A is A over A plus B times 100. Same goes for B. And there's some tedious calculations to do for this, but that's the summary. That's the picture view of this process. Now, most of this process, as a student, you just prepare the sample, you give it to me, I run it, and then you do these little calculations. And I'm going to show you how to do those in just a second. Let's talk about factors that affect the retention times and resolution of the components of a mixture. Just to reiterate what a retention time is, that's the amount of time between the moment that you inject the sample mixture into the column versus the time of that it takes for the component to make it through the column. So we hope for good resolution between the components of the mixture such that they're coming out at different times. And that's one thing that the computer's monitoring, is the retention time. How long does it take for a particular component to come out? And once again, I'm going to remind you that on the printout, you're going to see this as R dot T dot. That's the retention time in minutes. Resolution is just the same thing as it always is. How well do we do at separating the components of a mixture? With gas chromatography, it's really simple and easy to do that. Okay, so mixtures must be adequately resolved for gas chromatography to be useful. If they're not well resolved, then what we have to do is spend time figuring out these other variables: column length, carrier gas flow rate. All these things affect how well we resolve the components. And if we're having a hard time, we might want to consider affecting or changing the column length, for example. Typically, the GC instrument for us is 30 meters long, although Doug has to cut that down on a regular basis because problems happen, it gets dirty, or it breaks literally sometimes. The carrier gas flow rate is another thing that you could adjust. I don't do it at all, but helium is passing through the entire GC instrument 1 milliliter per second. If I'm having problems resolving the components of a mixture, what I might consider is reducing that flow rate to slow things down and give them a better chance to separate on the column. But perhaps the most important thing to affect the separation of mixtures is temperature. And here's where we have real control over how well we separate the components of a mixture. And so much so that we initially have a starting temperature of the oven, where the column is, and we can ramp up this temperature at whatever temperature increase that we so choose. And we can do probably up to 10 different temperature ramps and stabilize and all this kind of stuff. So we have a lot of flexibility when it comes to the temperature of the column, and so it can really custom tailor the temperature settings to get fast but also good separation of the components of a mixture. In fact, all the things that we run in our laboratory at this point, I've already taken the time to figure out what the best, most optimal settings are, and I save these as so-called methods. So everything we do in this laboratory at this point, I've already created a method for, and it's already got the appropriate temperature information. I really want to run them as quickly as possible, but also get good separation. That's the key thing. Welcome to the Shasta College Gas Chromatograph. I've already got a bunch of samples loaded onto the sampling tray. This is the robot arm that's going to eventually pick up the first sample, and the first sample is going to end up on the sample tray right about here. At that point, there's a syringe inside this big tower, which is going to first of all pre-rinse with pentane in this little solvent bottle, and then eventually it's going to tap into the sample and pre-rinse a couple of times with the sample. You can't see it inside here, but there's an injection port inside here, and eventually you'll see the syringe really pop down and inject the sample. At that point, we can't see this as well, but there's a big giant 30-meter column inside here that the sample flows through, and it's on that column that we get separation of the components of the mixture, and eventually they pop off one at a time into the mass spectrometer, which is here. This is our detector. This is how we see what's coming off the column. But that's the essence of what's happening in gas chromatography. I'm now going to show you an actual run of gas chromatography and talk about some of the details as we go. So right now I'm going to take you through method development for gas chromatography. I've pretty much developed all the methods I would ever need for the samples that we normally run, but just to show you how this works, there's a couple of important details when it comes to setting up a method. One is the oven temperature, so that's the first thing I'll show you. And I'm just going to go ahead and click that button. So right now it says oven, and depending on what the sample is, this sample requires 175 degrees Celsius inside the oven to start and hold that for 2 minutes. And eventually after 2 minutes, it's going to rise 30 degrees per minute, to a final temperature of 200, and then it's going to immediately rise 20 degrees per minute to 240. So it tops out at 240, and that's when the method is essentially over. So adjusting the temperature is really important, because if you don't mess with that appropriately, the run takes too long, or it's not long enough, and some real problems can happen with that. You just have to experiment based on the sample that you put in there. The other adjustments that are important are the injection amount. This is 0.2 microliters. That's pretty much the standard volume that I inject. That's a tiny amount of sample, but the syringes are tiny at the same time. The other important detail about this is how many times should we rinse the syringe? How many times should we pre-rinse with the sample about to inject? So you can mess with all those settings right here. I've pretty much got these set appropriately for this particular run. The only other thing that's important when it comes to method development for us is this factor right here. This is called the split ratio, otherwise known as a dilution factor. So right now for this particular sample, and I had to mess with this for many years before I got this right, it's set to 50:1, which means a dilution factor of 50. All these other settings that you see up here, I rarely have to mess with. The only one I think of significance, and I'm not going to show you right now, is the mass spectrometer itself, and there's some settings. Sometimes I mess with that, but not often. So temperature, dilution factor, and injection amount, how many washes to do, those are the important factors. Once I get them all set up, you save it as what we call a method. Methods are everything when it comes to gas chromatography. And now in the future, since I have that method saved, I can always use that method for this particular sample. I don't have to keep reinventing the wheel when I do this. So that's the essence of it. So now what I'm going to do is I'm going to show you an actual run, and what you're going to see is you're going to see the time start, and also eventually you're going to see the temperature rise. And this is always going to be a constant because the flow rate's a constant, but I could actually adjust that as well as the run goes. I'd never have to do that per se. And then I'm going to click on this window down here, which is called the chromatograph, and this is the important thing about how pure our sample is. Let's take a look at an actual run. I'm going to show you that now. I've already placed a sample in position number 11, so to run a single sample, I just click this button and I tell it the vial number. It's already set correctly at 11. I'm going to give it a file name. I'm just testing the run here. Test.d is the data file. The sample name is just test for now. Normally I would give this an actual name, like maybe the name of the compound I'm running or the mixture, and miscellaneous information. I'd probably put the person's name, whose sample it is, stuff like that. Operator name, that's me. I usually put that in eventually. But right now I'm going to just start the run. I've already developed the method for this sample, and it's complaining because I already have that data file, but I'm just going to overwrite it. So right now we're at t equals 0, and injection has not happened yet. So notice that the timer is not started until the injection has actually happened, and you won't see much of anything. So we're going to cut for a brief second until something happens. Okay, injection has just started and the timer has just started. Right now it's asking me to override the solvent delay. The solvent delay is a period of time which is currently set to 2.5 minutes where the detector is not on. The reason why we do that is because no sample is really reaching the detector. We may as well turn it off so we don't gum up the detector. So I'm going to say no to this. I don't want to override that. Right now the oven temperature is 175 degrees. The timer's already started. The flow rate's what is that? I think it's 1 milliliter per minute is what that flow rate is, or second, something like that. This is the chromatogram. Nothing is occurring on here. In fact, we won't see anything until we get to the 2.5 minute mark, and then we're going to start to see a GC trace at that point. We've reached the 2.5 minute mark, and the temperatures are already starting to ramp up. We don't see any compounds yet, but the detector is active. I can see that the voltage is on now. That means the mass detector is on right now. We don't see anything in the trace, so we'll probably, once we get to about 200, pretty soon, we're going to see the first peak spike in this sample, and I think that's the compound fluorine. We'll kind of wait and see. Okay, we just got our first little blip right here. That's the first compound in the mixture. There's just 2 compounds in the mixture, so the first one just came out at about 205 degrees Celsius, which is pretty hot. The second one requires an even hotter temperature. I don't think we'll see the second one until we get to about 230 degrees. We'll see what happens. Okay, the second compound just came out about 217 degrees. There's only 2 compounds in this mixture, so I'm pretty confident that the run's over. I'm going to prematurely stop this, and then we're going to take a look at the data analysis. So there's a separate program that works with the data. This is the run that we just completed. Here's the first compound. Here's the second compound. This is called the GC trace. And on the x-axis, what we have is retention time. 0 is somewhere over here. This axis actually started at 2 minutes. And at the 3-minute mark, the first compound eluted, and at the 3.7 mark, the second compound eluted. And the amount of compound in the mixture is proportional to the area underneath the curve, and so that's really the key analysis is I'm going to integrate these. First of all, I'm going to check to make sure that the appropriate setting is set, which it wasn't. Second thing we do is we just zoom in on this little peak, and I'm going to manually set the integration mark. And this little number that popped up there, that's the retention time detected by the software, and it's going to calculate the area underneath this curve. And then the other curve that I need to do is this one, so I'm going to manually integrate this one. And right now it says that the retention time for that one is 3.71. So the retention time is the amount of time it took for the compound to make it through the column and in the detector. So we're almost done. We've got this one integrated, this one integrated. We're not going to worry about the mass spectrum. It's next semester we'll talk about how to interpret that. But the mass spectrum actually tells you what the compound is, especially if I double click on the peak. I'm not sure what we're looking at right here. The last step is just to simply print out the data. And so I'm going to click percent report. And right now I'm looking at the report. And once I get home and scan this data, and I'm going to talk about how to analyze this data. But essentially for now, it's going to give us the area underneath the curve here and here, the retention times here. Later I'm going to show you how to work up the numbers, but that's how it goes. Okay, so here we're looking at an actual printout of data from last year, or maybe a couple years ago, I'm not sure at this point, but it was somebody's sample, I can't remember, yeah, it was a distillation, it was a fractional distillation, and here's the numbers that you need to kind of pay attention to. So all your mixtures in distillation, and column chromatography for that matter, just have two components of the mixture. I don't know what these components are, but I do know that this is the retention time right here for the first component. So it took 2.945 minutes for this first component to elute off the column, and then 4.717 minutes for the second component. And these are the two compounds. So peak number 1, this retention time. Peak number 2 is this retention time. And you need to note these times because this is how you're going to look up the appropriate response factors later, and I'm going to show you that in just a second. But the other number that you need to grab, and nothing else, is this number, which is called the corrected area. That's essentially the area underneath the curve, and then this area is for the second component. And notice that these two numbers are not the same. Likewise for the retention time. So these are two different components with two different areas. This is the only data you need. You're not going to use this at all. So don't even think about reporting these numbers because they have not been adjusted yet for the response factors. And we don't use peak heights because that's less accurate compared to areas. All right, so once you grab these numbers from the printout that I give you, and by the way, sometimes there's actually 3 peaks, and I just explained that for a second. If there's 3 peaks, that usually means that pentane is also registered in this printout, although I try not to include that, but just ignore it. Pentane is just a solvent. It sometimes pops up because we wash the syringes with pentane, but just ignore it. Now, this is a calculation helper. The way you get to this quicker rather than going into my slides is on the web page that has the GC talk, the video, you click on practice problems, the little radio button, practice problems, and then click submit. And you will get this in a concise way. And first of all, you choose the experiment. So this could be column chromatography or distillation. So we'll just click distillation, I guess. It's a little more complex. And all the mixtures are different for you guys. So you're going to have to figure out what your retention times are for the two components. I just talked about how to find that on the printout. So the retention times are whatever they are. So you click, maybe this is the retention time for the first component. And then secondly, the second retention time was this value. And it automatically pops up in these two boxes down here what those response factors were. Now, if that's still not the right set of response factors, or you couldn't find a particular RT, you can manually plug in the response factors if I've told you what these are. Otherwise, these are already put in for you based on retention times. Now, here's where you have to manually enter a value. And so I'm just going to make up values here for a second. So I put in 456 for the first one and 654 for the second one. Truth be told, these are much larger values in actuality, so you're going to see that the corrected areas are ginormous values, but so be it. Okay, and then you just simply click calculate the percentages, and it just does all the hard work for you. So it is in fact performing those calculations that I talked about earlier, and that's how you quickly and simply calculate the percentages of A and B. Now, I didn't specify what A and B are because obviously this is 3 different experiments with bunches of different unknowns, so you have to kind of figure out on your own what A is and what B is. So, for example, distillation, Distillation, it's based on the boiling point temperature, so that's a different set of data. That was your temperature versus distillate collected or time based on the computer program. So you just figure out the boiling points, you look them up that way. You're not going to get the identities from GC data. It's just simply not going to happen. All you're doing here is figuring out the relative percentages of the two components. Now, for column chromatography, test tube number 2 should contain fluorine. Test tube number 3 should contain fluorinone. And then another experiment we'll do this semester, more than likely, is competing nucleophiles, and I'm going to talk about that later, so I won't talk about it here. But this is it, you know. So you just get that printout, you do this little thing, and that should be it for calculating the percentages of the components.